Hello Internet, and welcome to Curious Stick. And let's face it, we've all had it up to here with hearing. It's not the heat, it's the humidity. Thanks, Aunt Kathy, that's a lovely saying. But unless humidity is physically wringing the sweat out of my body, I'm gonna need a slightly better explanation. Every summer we're told the same things. Drink plenty of water, stay in the shade, wear light-colored clothing, use a fan. And while all of those are good pieces of advice, almost nobody ever explains why they work. Because here's the thing, if you want to beat your enemy, you first have to understand your enemy. And today's enemy is heat. Now, before we dive into the science, let's clear up a few common misconceptions. Let's rapid fire these. Fans cool rooms? Not exactly. Leaving your freezer open cools your house? Definitely not. Metal is colder than wood? Usually false. Heat and temperature are the same thing? Nope. And of course, it's not the heat, it's the humidity. Well, kind of. By the end of this video, every single one of these statements is gonna make sense. But before we can understand heat, we have to understand why humanity spent thousands of years misunderstanding it. For most of history, people didn't actually know what heat was. And by the 1700s, scientists had mostly abandoned Aristotle's idea that heat was one of the classical elements. Instead, they proposed something that, surprisingly, wasn't all that different. They imagined heat was an invisible fluid. Seriously, it was called caloric. The idea was simple. Hot objects were full of caloric. Cold objects contained less of it. Heating something meant pouring more caloric into it. And conversely then, cooling something meant letting caloric leak back out. And honestly, if nobody had ever taught me modern physics, I might have believed it too. It explains quite a lot. Put a hot poker into cold water. The poker cools down. The water warms up. It certainly looks like something invisible flowed from one object into the other. The theory worked until one day someone started drilling cannons. Meet Count Rumford. While supervising the boring of large brass cannons, Rumford noticed something strange. The longer the drill turned, the hotter the cannon became. And it didn't stop. As long as the drill kept moving, more and more heat was produced. Now, think about that for a second. If heat were really an invisible fluid stored inside the cannon, eventually, the cannon should run out. But it never did. As long as there was motion, there was heat. That single observation shattered one of the biggest ideas of science. Heat wasn't some mysterious substance hiding inside the objects. It had something to do with motion. A few decades later, another scientist named James Prescott Joule took that idea even further. He built an experiment where falling weights spun paddles inside a container of water. Nothing chemical was happening. The paddles simply stirred the water. Yet, the harder they stirred, the warmer the water became. For the first time, scientists had convincing evidence that mechanical work could become heat. Heat wasn't matter. Heat was energy. That discovery completely changed the way we understood our world. Today, we know that every object around you is made of atoms. Tiny particles in constant motion. In a solid, they vibrate. In a liquid, they slide past one another. In a gas, they fly around freely. The faster, on average, those particles move, the greater their kinetic energy. And the greater their kinetic energy, the higher the temperature. But here's where almost everyone gets tripped up. Temperature and heat are not the same thing. So, if heat and temperature aren't the same thing, what's the difference? Well, imagine you and your friend each have a jar filled with marbles. Your jar has 10 marbles. Your friend's has 1,000. Now imagine I shake both those jars with exactly the same intensity. The marbles inside both jars are moving around with roughly the same amount of energy. But which jar contains more total energy? The one with 1,000 marbles. Heat and temperature work in a surprisingly similar way. Temperature tells us how energetic the particles are on average. But thermal energy is the total amount of energy stored in all those particles combined. A bathtub and a mug of coffee can both be 40 degrees Celsius. They have the same temperature, but the bathtub contains far more thermal energy because it contains far more water. Now, here's where things get really interesting. Heat isn't something an object actually has. Heat is something an object does. More specifically, heat is thermal energy moving from one place to another. That's it. It's a transfer. Whenever two objects have different temperatures, nature tries to balance things out. Put an ice cube into a warm drink, heat leaves the drink and enters the ice. Leave your coffee on the kitchen counter, heat leaves the coffee and enters the surrounding air. Stand barefoot on scorching pavement, heat leaves the pavement and, well, enters your feet. Have you noticed anything yet? Well, aside from your bare feet getting really uncomfortable on the hot pavement, heat always has a direction. It naturally flows from warmer objects towards cooler ones. Not because it has a brain, not because it wants to, but because that's simply how energy spreads throughout the universe. Just like adding a drop of food coloring into a glass of water. At first, it's concentrated in one place. Given enough time, it spreads out. Heat behaves much the same way. It always moves towards equilibrium, toward balance, and only has a handful of ways to get there. It can move through direct contact, through moving air or water, through invisible electromagnetic radiation, or, in the case of your body, by hitching a ride on evaporated sweat. Those four methods are called conduction, convection, radiation, and evaporation. And understanding them is key to understanding why some summer days feel unbearable, and more importantly, how to fight back. So, if the heat is our enemy, how exactly does it attack us? Well, despite what it might feel like on a sweltering summer afternoon, heat isn't particularly creative. As we mentioned earlier, it only has four ways of getting from one place to another: conduction, convection, radiation, and evaporation. Master these four, and you pretty much mastered heat itself. Let's start with the simplest: conduction. Conduction is heat moving through direct contact. Touch a hot frying pan, your hand gets burned. Sit on a sun-baked bench, your legs get burned. Hold an ice cube, and your hand gets cold. Although, as we've just learned, the ice isn't sending cold into your hand is sending heat into the ice. Now, remember one of the misconceptions from earlier? Metal is colder than wood? Well, not exactly. Let's do a little experiment. Leave a metal spoon and a wooden spoon sitting on your kitchen counter overnight. By morning, they're almost exactly the same temperature. So why does the metal spoon feel colder? Because metal is an excellent conductor. It steals heat from your hand much faster than wood does. Your brain isn't actually very good at sensing temperature. What it's incredibly good at sensing is the speed at which heat is leaving or entering your body. The faster heat leaves your skin, the colder something feels. The faster heat enters your skin, the hotter it feels. That's why grabbing a metal handrail in winter feels like grabbing a block of ice. The handrail isn't necessarily colder than the wooden fence right next to it. It's just much better at pulling heat out of your hand. Now, let's move on to convection. Convection is what happens when heat hitches a ride on moving liquids or gases. Warm air rises, cool air sinks. Not because heat rises, but because warm air expands. When air gets hotter, the molecules move around more. They spread farther apart. That makes the air less dense than the cooler air surrounding it. The cooler, denser air sinks beneath it, pushing the warmer air upwards. That's convection. And that brings us to another misconception. Fans cool rooms. Well, not really. A fan doesn't create cold air. It simply moves the air that's already there. So, why do we feel cooler standing in front of one? Two reasons. First, it blows away the thin layer of warm air that's constantly building up around your skin. And second, it helps your sweat evaporate faster. We'll come back to that second point in a minute, because it's far more important than most people realize. But here's the interesting part. If nobody's in the room, the fan isn't cooling anything. In fact, thanks to the electricity powering the motor, it's actually adding a tiny bit of heat to the room. Not much, but enough that, technically speaking, a fan is a very bad air conditioner. It's a fantastic people conditioner, and that's a pretty important distinction. Now, unlike conduction and convection, radiation doesn't need anything to carry it. No air, no water, no physical contact, just empty space. Which is a good thing, because if heat needed air to travel, the Earth would be a frozen rock. The sun is almost 150 million kilometers away, and between us and it is mostly empty space. So how exactly does its heat reach us? The answer is electromagnetic radiation. Visible light, infrared light, ultraviolet light. They're all members of the same electromagnetic family. When sunlight reaches your skin, some of that energy gets absorbed. Your atoms begin to move a little faster. Their thermal energy increases, and suddenly you're warmer. That's radiation. It's also why standing under a tree feels so much cooler. The air temperature might be exactly the same, but you've removed one of the biggest sources of incoming energy, the sun itself. Remember another misconception from earlier? Black attracts heat? Not quite. Black doesn't magically pull heat towards it. Instead, black surfaces absorb much more of the sun's radiation than lighter colored surfaces. White clothing reflects much more of that incoming energy. Black clothing absorbs much more of it. That's why dark cars become miniature ovens in the middle of summer. They're not attracting heat. They're absorbing more of the energy arriving from the sun. And speaking of ovens, let's settle another misconception. Leaving your freezer open does not cool your house. In fact, it does the exact opposite. Remember when we said heat always flows from warmer things to cooler things? A refrigerator takes advantage of that. It removes heat from inside the freezer, then dumps that heat somewhere else. Have you ever felt the back of a refrigerator? It's warm. That's because all the heat taken from your food ends up there, along with extra heat produced by the compressor doing all the work. Now imagine leaving the freezer door wide open. The refrigerator starts pulling heat out of your entire kitchen, only to dump that same heat, plus a little extra, right back into the kitchen. Congratulations, you just turned your refrigerator into a very expensive space heater. But none of it, comes close to your body's greatest weapon against heat, sweat. Which finally brings us back to Aunt Kathy. It's not the heat, it's the humidity. Turns out, she was onto something. See, sweat doesn't actually cool your body. Water sitting on your skin isn't doing very much. The magic happens when that water evaporates. Changing from liquid into gas requires energy. Lots of it. And where does that energy come from? You. Every drop of sweat that evaporates steals thermal energy from your skin before floating away into the air. It's an incredibly effective cooling method. In fact, it's one of the reasons humans can run for such long distances. But there's one problem. Evaporation only works if the air can actually accept more water. On a dry day, sweat evaporates quickly. You cool down. On a humid day, the air is already packed with water vapor. There's less room for your sweat to evaporate. It stays on your skin. It drips off your body, and suddenly, your best cooling system starts breaking down. Humidity doesn't make the air hotter. It makes you worse at getting rid of the heat. So maybe Aunt Kathy deserves a little more credit than I gave her. So, now we know what heat is. We know how it moves. We know how it reaches us. But what happens once it gets inside our bodies? Well, despite what it might feel like on a scorching summer afternoon, your body is actually incredibly good at dealing with heat. In fact, every second of every day, it's fighting to keep your core temperature at around 37 degrees Celsius. Think of your body as having its own built-in climate control system. The moment your brain notices your temperature starting to rise, it immediately gets to work. First, it widens the blood vessels near your skin. This process, called vasodilation, sends more warm blood from your body's core towards the surface of your skin. Why? Because your skin is where heat can escape. It's essentially your body's radiator. Next comes your greatest weapon, sweat. And remember what we learned earlier? Sweat itself doesn't cool you. Evaporation does. Every drop of sweat that evaporates carries thermal energy away from your body. It's one of the most efficient cooling systems found anywhere in nature. Your heart joins the fight too. As more blood is sent towards your skin, your heart has to pump faster to keep everything moving. Your entire body begins working harder, just to stay the same temperature. It's an incredible balancing act. But here's the problem. Every cooling system has its limits. If the air is too hot, if the humidity is too high, if you become dehydrated, or if your body simply can't get rid of the heat as quickly as it's gaining it, that balance starts to break. At first, your body enters what's known as heat exhaustion. You'll often feel dizzy, weak, nauseous. Your head might start pounding. You'll probably be sweating heavily. Your heart races as it works overtime. This is your body's warning sign. It's telling you that the battle is becoming harder to win. And if you ignore those warning signs, things can become much more serious. Heat stroke isn't just being really hot. It's a medical emergency. As your core temperature climbs to around 40 degrees Celsius or higher, your body's cooling system can begin to fail. Your brain is especially vulnerable. Confusion, disorientation, slurred speech, loss of consciousness, these aren't just symptoms of being uncomfortable. They're signs that your body is no longer able to protect itself from the heat. Without rapid cooling and urgent medical treatment, heat stroke can permanently damage the brain and other organs, and it can even be fatal. Fortunately, everything we've learned in this video gives us the tools to stop things from ever reaching that point, because now we don't just know what heat is, we know how to fight it. So, how do we beat the heat? Turns out, it's actually pretty simple. Not because heat is simple, but because heat always plays by the same rules. Stay in the shade. You've just blocked one of the biggest sources of incoming heat, radiation from the sun. Wear light-colored clothing. Instead of absorbing as much of the sun's energy, you're reflecting more of it away. Drink plenty of water, because your body's greatest weapon against heat, sweat, only works if you have enough water to replace what you've lost. Use a fan, not because it's making the room colder, but because it's helping your body get rid of heat by moving warm air away from your skin and helping sweat evaporate. If it's cooler outside than it is inside, open the windows. If it's hotter outside, keep them closed. Because remember, heat always flows from warmer places toward cooler ones. And maybe don't leave your freezer door open hoping to cool your house, unless your goal is to make your energy bill cry. The point is, every piece of advice you've heard about staying cool has a reason behind it. And once you understand that reason, you don't have to memorize the advice anymore. You can figure it out for yourself. Because whether you're choosing what clothes to wear, trying to cool down your house, or deciding whether that fan is actually helping, you're no longer guessing. You're thinking like a physicist. So was Aunt Kathy right? It's not the heat, it's the humidity. Well, kind of. Humidity doesn't make the air hotter. It makes your body's best cooling system less effective. So on those sticky summer days, when it feels like you're melting, you're not imagining it. Your body is simply losing the battle to get rid of heat. Fortunately, now you know exactly how that battle works. Because heat isn't magic. It isn't an invisible fluid. And it certainly isn't out to get you. It's simply energy, following the laws of physics. And now, so can you. Till next time. If you enjoyed this video, remember to subscribe so we can keep bringing you valuable content like this.